And AP Calc, 6.2 definite integrals, part 2. Let's go. Constant functions. Straight lines. Integrals of constant functions are easy to evaluate. Over a closed interval, they're simply the constant times the length of the integral. So, if this C represented a height, f of x equals 2. Well, that means it's 2 right here, it's 2 right here. All you need to know is whatever b minus a is, 7 minus 5, if that's, you know, a 5 and stuff. You figure out what the base is times the height, and that's the function's constant. If it's below the x-axis, you'll get a negative area on here. And if you truly want the area, not just the value of the integral, you're going to have to flip the sign. And that's where this comes in. If you're looking for area A, take the negative value of whatever you compute. Now, example 3. I refer to physics examples because most of you have taken some physics or are taking physics. In grade 10 you had an introduction, and that's the most common application to these problems on an AP test, in a calculus book, and most of you have experience with speeds and distances and accelerations. So we tend to use these kind of things. Revisiting this train problem here, we'd seen a while back. The train moves slowly at a steady 75 miles per hour. It's important it says steady because it's not going up or down. It's on cruise control. From the time 7 a.m. to 9 a.m. So no tricks, they didn't turn to p.m. or something like that. So 2 hours. Express its total distance traveled as an integral. Evaluate using theorem 2. Now, I'm going to draw a sketch of this just so we understand this too. So, 75 miles per hour, that's our velocity here. And miles per hour. Now, the hours. Let's just call 12 noon 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's all I need on this graph. And it's constant, 75, so we understand this. I don't know when it started being constant, but we're going to steady at least over 7 through 9 anyways. Express its total distance traveled as an integral. So this is the time in hours here. Okay. So basically it's the line at x equals 7, line at x equals 9. We're finding that area bound by the axis, 7 and 9, x equals 7, x equals 9, and y equals 75. So this turns out to be a rectangle. Now, what is the integral? Our x, we'll use like a t, I guess. I guess I'll go back to here. We're going to integrate from what to what? What is like my x, t values in this case? 7 and 9. How rude. You're eating, talking. Anyways, I know you're self-conscious. And the function is a constant function. It's 75, right? V equals 75 at any time that we're told of, at least in this portion of the problem. I'm sure the train stops eventually. Now, normally we'd put dx, but since we're talking maybe about times, you'd call this time t. So I'm going to put dt, just so you get used to seeing things without axes. Okay? dt. Now, I don't really know, given this, at this point you might be saying, I don't know how to evaluate this using raw calculus methods. But I do know, because I know the graph, I do know the shape, and I do know how to find the area. And that will give me the displacement. And we can tell by the units. The area will be what we're looking at. So, what is the height? 75. It's a height of 75 times. I'm going to put in the units, just humor me for this here. Miles per hour. Times the change in time, 9 minus 7, so 2 hours, agreed? What do you notice about the units when you do that? Cancel out the hours, we get miles. And we want a displacement. It's a positive. Moving, if I said the positive direction is north, then it moved 150 miles to the north. In the positive direction, whatever that may be. Now, that's the theorem 2 up here, the area. It's just, if you know how to find it for a constant, it's just a rectangular area. It's not a big deal. So that's a simple equation. I'm going to just flip her. Are we good? So, discontinuous. Remember how we said something's integrable, it implies it's guaranteed to be able to be integrated if it's continuous. Sometimes, even if it's discontinuous, you can do the integral as long as it doesn't go off to infinity as a general rule of thumb. And in this case, it doesn't. So, I just mentioned this. Continuous functions are integrable. That's guaranteed. There are some. Okay, I'm just repeating. That's basically what it says. We have the absolute value of x divided by x. You plug in negative numbers into this. So just think of this. Well, negative 2 is absolute value over 2. Comes out to be, oh, negative 2, though I didn't put that in there. But, right? That's going to be negative 1. And all the positive numbers are always going to come out to be plus 1. So when you graph this, you have a line at negative 1. You have a line at plus 1. What about 0? Undefined here, undefined here, right? You guys get that? Because you get it. It's in 0 over 0. Indeterminate, right? So it's definitely discontinuous there. And as a matter of fact, we don't have a value right at 0. However, does it make sense that we could do the area right up to 0 here? We can do the area right up to, not your way. This area here, add those areas. Whoa, wait. Anyways, if you add those two areas, if you break it up into a 2-part problem, you should be fine, right? So, essentially, what we're saying is that I can evaluate this integral. I can't do it as one big shot. No. But I could do it as 2 chunks. I could go from negative 1 up to 0 for this function. Oh, I should have put something down there. Oh, you see how that resets on disappearing hand on me sometimes? dx. Ah, what am I thinking dx? That's how I did this in the first place. X dx. Now it'll be the area here, like I just said, in this box, or I said the area, the integral there will be the negative area. It'll come out negative. Plus the area, or the integral from 0 to 2. So I'm talking about this top area, which is hard to see the red on black. Okay, so we got those 2 areas, or those 2 portions. I shouldn't say area because we're going to use negatives in this, aren't we? Now, using negative signs, because we're talking integrals. This portion, from 0 to negative 1, that's the height. We're going to say it's a height of negative 1, we'll think of it, because it goes down. And a span from negative 1 to 0, that's a span of 1 unit, right? Because here's 0, here's negative 1. This goes up to 2 here. Okay, on the other side. So, what do we got for an area? We've got negative 1 times 1, right? Everybody agree with this? This chunk here, negative 1 times 1, it's negative 1. Plus, we'll get positive area here. It's a base of 2, because it goes from 0 to 2 overall, and a height of 1. So the area is 2 times 1, it's 2. So the arithmetic is hard. Negative 1 plus 2. That integral has an overall value of 1. The negative area plus the positive area, right? You have more positive area than negative area. Whatever that may mean. It might be money lost and gained at certain times. It might be a distance thing. Who knows what this could represent. But are we good with that? Doing areas when it's simple. Now, explain why this function is not continuous on 0 and 3. What kind of discontinuity occurs? Quick check. I hope you could see here, you do a quick scan. What's the technique you use right away when you see something? I think that's factorable, you say. I hope so. Yeah. Let's factor it right away. So that's equal to x plus 2 minus 2. Okay. Because the function isn't continuous here because you have 0. You have an indeterminate spot there, right? Yeah. What kind of discontinuity is this? If you can factor it out and remove it. It's a point discontinuity or a removable, you can think of it as too, right? If you can remove it, it's just a hole. It's a point discontinuity. Removable discontinuity is same thing, right? So, removable discontinuity. At x equals 2. And I proved that I can remove it by faction, right? If you graph that, that would really be the straight line, x plus 2, with a hole, and you get to x equals 2, a point. Discontinuity or removable. Either one if you want to use those words. Now, same function. Use areas to show that x squared minus 4 over x minus 2 dx from 0 to 3 we're evaluating is 10.5. And then use areas to show a different one, integer. I won't talk to you. Well, I'll talk to you about that. Yes, okay. Now, this is what's given. So we still have to think of this as x can't be 2, right? Always go with the given function for domain values. Even though I know it tidies up, and really it's x plus 2 is what it's a straight line. So use areas to show that. I'm going to do a quick sketch. X plus 2 starts at the b value is 2, and then it's a slope of 1. So all I'm going to do is a quick sketch. There's a hole at 2, and I'm going to go to 3. From 0 to 3. According to this hole, then, where do we have to break things up to 2 integrals? At 2. This happens at 2. All you have to do is the area from 0 to 2 plus the area from 0 to 3. So you could do it a number of ways. You could do it as cutting this up into a triangle and a rectangle there, a triangle and a rectangle then underneath, right? Can you guys remember how to do, though, just incidentally? It's called a trapezoid. Take the average, yeah, the middle value of the two heights. Now, what he just said, I think, what he's saying is that if this is a height of 2, and at 2, what would you get? You would get a height of 4, even though that doesn't exist. This area here under the trapezoid is the same as the area under a rectangle with the same base, but a height midway in between here. There's as much below as there is above missing from that. So we kind of take the average of this. There's one way to find the areas. And you'll get more familiar with that. Now I'm going to try to fit this in here. So, number 2. I'm going to say I'm going to do the area from 0 to 2, because that's continuous until that point, of the function x squared minus 4. Add that to the area from 2 to 3. What is that area? How do we go about doing that area? Well, there's a number of ways. If you do remember how to do the area of a trapezoid, go ahead and do that. I'm going to just do it quickly because I don't think everybody remembers at this point, right? We'll come across it right away. So let's do it here. This green rectangle here has a base of 2 and an area, or a base of 2 and a height of 2, right? Because this starts at x plus 2 starts at 2. So the area will be 2 times 2, it's 4. If you could plug 2 into this equation here, and it's really just x plus 2 here, right? I get 2 plus 2, that's a height of 4. So that's another, it's a triangle with a height. It starts at 2, goes up to 4, so it's a height of 2. 1/2, 2 times 2, agreed? 1/2 base times height. So this little triangle is an area of 2. Then the next portion, height of 4 times a width of 1, so an area of 4, right? Stop me if I make a mistake. And because the slope is only over 1 unit, it only goes up 1 higher. So it's a height of 1 for the triangle. Because if I put 3 into there, it's 3 plus 2 is 5, right? And a width of 1, so 1 times 1, take half of that, it's 0.5. So that's the area of that little triangle. So we add them all up. 4 plus 4 plus 2 plus half is 10 and a half. Would we agree? I'd say so. So that just verifies our answer. Now, have you guys ever played around with the integer function on your calculator? Yeah. Doesn't matter anyways. Whatever it is, it just takes, if you put into this function here, integer x, and you put an integer 0.5, it will just chop it off and call it 0. It doesn't round it up or down. If you said integer 2.7, it'll just call the value 2 until you get to 3.0. Then it'll call it 3. 3.1 is integer function on your calculator. It'll just return a 3. It just chops it off. It doesn't round it off. Okay? That's all it does. It gives you chopped off values. Truncate. So really, this is like it looks like a set of stairs when you do it. And we don't necessarily have to calculate it, but I'm going to squeeze it in here. What does this look like from 0 to 5? Well, the first portion would be 0 till 1. It'll be just sitting at 0, because 0.2 would be chopped off as 0. So here's 1. Then, at 1, it'll start, the integer function would give you 1. Until you get to 2. This is 1. And 2. You guys get this, I think? Okay. What the function represents. It looks like a set of stairs as you do it all the way up to 5. Now, I ran out of space, but I think you can imagine how it steps up and then steps up. Some people call it the steps up function. I think it's also called the Heavisides function. Anyways, it's not too complex, but it's actually useful for some things. But what's the first area from 0 to 1? 0. The second area is 1. Yeah, I'm going to keep track with my thumb. And then from 2 to 3, the area, it's a height of 2. So it's 2 plus the initial 1 that you had there, right? You got a total of 3. So what's the area between 3 and 4 going to be? Height of 3 over a span of 1. So 3. So 3 plus 3 is 6. Okay. And then that was 3 to 4. So 4 to 5. Height of 4. 6 plus 4 is 10. It does work, doesn't it? Okay. Now I didn't draw that out, but we kind of reasoned it out. Now the reason being is that I want to just take a look at a few of the things in the next page. How many people other than one person I know, anybody else get up to 33 yesterday? You'll have more time to work on this. But I want to work on these as a group. So you can take back. Okay, so your next page, and this is, by the way, this whole unit for the most part, most of this, if not all of this, is AP material. It's adding and stuff like this, but just so you know. Now when I say LRAM or RRAM and MRAM, there are types of Riemann sums. The L refers to the left side, the right side, or the midpoint. Okay? They're types of Riemann sum approximations. And really the RAM stands for left rectangular approximation method. Okay? Now I want you to take a look at this. This is really an example with notes here first. 0 to 2. For this function, 2x minus x squared. That can be approximated. Let's go with a left approximation. 4 intervals as shown below. And I've taken this from 6.1 section. 6.1, question 5. Now, if I break it up into 4 intervals, that means I'm going to plug in the first, second, third, and fourth value on the left side, 4 consecutive ones between 0 and 2. Now, I think I chose something that's small so that you can see this. And I'm going to erase this in a minute here. But from 0 to 2, if I broke that up into 4 intervals, we've got half. I used the fraction. So 1/2, and I got 1, and I got 3 halves, and then 2. Everybody sees that. Now, if you want to jot that up at the top, it might come in handy. But this is where I'm coming from. The first interval for this function, 2x minus x squared, what's the left side of the first interval? 0. So what am I going to do? I'm going to plug 0 into this equation to get the height at the left side. 2 times 0 minus 0 squared. I showed that, though. I know normally you just say 0. But I want to show you why I'm doing that. Then, the next interval. I purposely put the starting value plus half, okay? Because I'm climbing up by half each time, right? So, you'd never show your arithmetic this way, but I'm trying to show you something. So 2 times 1/2, right here, half squared, minus half squared. That's the second value. That's the second value. The third value is this interval here, and the left side of that interval is the number 1, right? So I plug in the number 1. I have it shown here too, simplified a different way, right? Here's the half. Then the next interval here, the fourth interval, the left side is 3 halves. Now this is probably what you would have jumped into, is actually the second one, right? That gives you the height of 4 different rectangles. What's this half at the end? Because it's big brackets, and I'll come back to the top line after. But because we've only got the heights. Is the base, the width of the base changing each time? No. It's always a half a unit wide. So this means this is half times 0, half times this value, half times this value, right? But why write it all those times? We could factor it out. Take all the heights times 1/2. That's what that means. Okay, now I'm going to revisit though up here. It gets confusing. Because why the heck did I do it this way? Just think of it this way. Each time I'm climbing up by half a value, or half of a unit. So I've got 2 times 1/2. Now I square it for this one here, or I multiply it by 2. The next time, I'm talking about this value. How many groups of 1/2? I've went 1, 2, 3. 3 times the interval of 1/2. That's not absolute value. I was just trying to highlight these numbers here. So do you see? I'm kind of working backwards there. This is where this comes up. And then you creep up. And I use this value. I've used the left side of all 4 of the widths, strips. Now, there's nothing to figure out on here. I'm just trying to show you where things come from. Where does this half come from, especially when it's larger and you couldn't just look at 0 to 2 and reason this out? How wide is the whole span? 2, because you're going final minus initial. 2 minus 0 divided by, so where does this come from? It comes from 2 minus 0 divided by how many sections or subintervals did I say to use? 4. That's where that came from. Okay? So each time, each interval will have a width of 4. Okay? And you're climbing up by 4. The first value was the 0 value. Then you climb up by 1 over 2 out of 4, 1/2. A second group, 2 groups of 1/2 added to that value. 3 groups of 1/2. That's one way to think about this. Now, that's the subintervals. Also, I made it so that sometimes you notice that I put the 0 plus. This is your starting value in general. Okay? So I put that in here and I forgot to mention all of these. That's your starting value. And I'm not going to point out all the others. We start at 0. Because what if I change this to go from 3 to 5? Now, I just put that in green. It's not going to stay there. 5 minus 3, if I look at this, the interval part will still be the same. It'll be 5 minus 3 divided by 4. Right? It'll still come out to be half. How would you know what you're starting at? Well, the first value you'd plug in would be, and I'll use green marker and then erase it, 5. This would be the same, right? Then the next one would be 5 plus 1/2. 5 plus 1/2, right? 5 plus 2 groups of 1/2. 5 plus 2 groups of 1/2. You'd just say 6, right? And so on. So usually you don't see that. Oh, I want to do that. You don't see that because we don't usually write in the zeros. But I wanted to for this example. I said I was going to erase what I have in blue here. Let's try this. Now, using that as kind of a pattern. Rewrite the integral 2 to 5 for x squared dx as an integral, using our round approximation, so a right Riemann sum, involving 6 subintervals. Don't evaluate and don't have any decimals, only use fractions or integers, okay? So the first thing we should figure out is, what is my interval spans? Now you could think about this, but I'm going to explicitly write it out. My interval width. Are all going to be 5 minus 2 divided by 6 intervals, right? So really I'm asking myself, how do I take 3 units from 2 to 5, so 2, 3, 4, 5. And I separate that into 6 intervals. Once again, it comes down to a half. Try to keep the math easy. Halves, thirds, quarters, stuff like that. Okay? Does that make some sense? If you chop up 2 to 5 into 6 intervals, you're going to be going up by half each time. That's what we're saying. And that'll be that tail end number. So like the dx. Okay. So this is like the dx, what we just found, except dx refers to an infinite amount of strips of 0 width. Then, what else? Well, the area. Area will be equal to the function evaluated at, I'm going to use a big bracket. Now it's just x squared this time is the function, right? We start at, what is the right side of the first interval? Now if you want to think about it, we can because it's small. Because I'm just going from 2 to 5, and I've got 2, 3, 4, 5. So yeah, 2.5 is the right side. But the way I'm going to show it is like this. 2 plus a half squared. Why? Because it's going to seem easier in the long run. Plus, the next interval will have the right side will be 2.5 to 3, so it'll be 3. But I'm not going to show it that way. I'm going to show it as 2 plus 1, 2 groups of a half, right? So I'm actually going to write it out like this. 2 groups of 1/2 squared. You got this? The initial value plus 2 changes in value, right? And you can see I'm going to have to make mine smaller because I've already practically run out of space. But nothing was wrong. So where was I? 2 plus a half squared plus 2 plus 2 groups of a half.
Are you just doing this to show a point, or should we actually like going out of this every time that?
No, not every time, but you're gonna see why when you get these. So yeah, this is actually 3 squared, is what you see. Yeah. But you probably won't have problems presented to you simplified. You might, but I think you can identify those. 3 groups of a half squared. So I'm up to here now. I need 3 more, and I'm going to erase this because I'm going to need this space. Starting at 2 and 4 groups of a half, whole thing squared. 2 plus 5 groups of a half squared. 1, 2, 3, 4, 5. 2 plus 6 groups squared. So I've gotten to 5 now. End the bracket. Those are all of the heights, right? Times the width of each interval, 1/2. Now, I want you to see, if it makes you feel better, you can rewrite it as 2.5 squared plus 3 squared plus 3.5 squared plus 4 squared. You don't have to. But the reason why I wanted to do this is let's make some connections here. If you were given this, could you come up with this expression here? This sum represents a right Riemann sum for the integral. Well, let's just see. This is like the dx, but it tells you each interval is a half wide, right? What value did we start at? 2. Okay, so that's where we get this. And we went all the way up. Even if it was simplified and it said 2.5 squared plus 3 squared plus 3.5 squared, blah, 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 all the way up to 5 squared, right? This is 5 squared. The ending point, if you recognize that they are right sides, is 5. So that's where you come up with this. Doesn't it look like each time you're squaring whatever you put inside? So that's how you come up with the x squared part of this. If you're given this summation. And you will be given problems sometimes that look like this. They may be giving us 2.5 plus 3 plus blah, blah, blah. Maybe like this, and it's easier to figure out what's going on. Now this is abstract, not totally abstract, I guess, but this is different. Yes? Like this part? Okay, the first interval, it starts at 2, but I said the right side of the interval, so 2 to 1/2 larger. Each time we're going up by 1/2, and that's what we figured out right there. And then the next value, 2 plus 2 groups of 1/2 for the second value. For the third value, plus 3 groups of 1/2. Just to see, you could see the pattern better when I show it like this than if I had put 2.5, 3, 3.5, 4. Now, what if we're given this kind of notation? Now this is where it gets tricky. And I'd say this is why I invented this page this year. Last year students were weaker on this and I was weaker on this. Now you can sometimes come up with an expression of 2 or 3 integrals that will give you the exact same expression, or the same value. So there's more than one answer, but there's sometimes one really obvious answer here. Now, this part of it tends to be the same. It says an infinite number of strips. So this would be 1 over an infinite number of strips. Well, that doesn't help. But remember how we were saying above here, you know, plus 1 group of 1/2, 2 groups of 1/2, blah, 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 right? That half, it's really easy if it matches what's at the tail end, the dx. That half was like the dx in there. This summation means 3 plus k groups of 1 over n. Many times. 1,000? No, more than that. 1,000,000, more than that. An infinite number of times. We can't count. But do you notice that this is really k times 1 over n? Okay, it's telling you to start at 1, 3 plus the first group of 1 over n, plus the second group of 1 over n. If it helps you, just pretend and say that n is approaching 10 or something like this. Then this is 1/10. The first times 1/10, the second times 1/10. What does it look like the starting value is on this one? 3, right? What does it look like the function is? So let's just do what we know here. It looks like it starts at 3. What does it look like the function is? What is it telling us to do operation-wise to whatever you get inside the bracket? Square. So this would be like an x squared, dx. Now, keep it in mind. This thing here, the 1 over n. How did we come up with 1/2 here? We said whatever the span is, divided by the number of things in the interval, right? If there was 4, it'd be 1 over, or it would be 2 over 4 for this one, or 2, is what it's simplified to. But here we say it's n. It could be 10, it could be 1,000,000. Well, it's actually approaching infinity, right? Whatever. But 2 minus what? Or, I'm sorry, 3 minus is where we're starting from. I should say it the other way around. Something minus 3 gives us 1. So it's from 2 to, or I keep saying 2 for some reason. 3 to 4. You see that this is, as long as this is an exact match here, we can say it must go up by 1 unit. This represents 3 to 4. This integral will give you the same value as this. Now this is tricky, and I know. That's where that came from. Now I'll just draw arrows here. That's where that came from. Something squared, that usually people can identify fairly easy, right? So, yep.
P over n and 1 over n are the same?
This means, yeah, Kind of. I'm going to rewrite this then. And just,
Does the 5 do anything?
oh, 5 times 5x squared. Thank you.
5x squared, okay.
Sorry. The constant out in front is 5. I missed that. Working on the other stuff. You're right. 5 times something squared. Now, I'm getting back to Mr. LaBelle's question here. The k over n. I'm just thinking of the function part here. So I'm going to skip the limit thing. But what you're wondering is 5 bracket. How do we think of this? I think of this as k times 1 over n, then square it. Do you notice that as long as this term and this term are an exact match, what's the starting value of k? It's 1. Then 2 groups of 1 over n. Then 3 groups of 1 over n, up to an infinite number of groups, right? Now, infinite is not a good thing to think about, so if it hurts your head too much, just pretend that n is approaching 5 or 10 or something like that. And you just say, well, if this is 1 over 10 here, this is 1 over 10 here. Oh, I didn't mean that, right? Think it's then 1 group, 2 groups, up to 10 groups. What would that up to, you know? Like 10 groups times 1/10. It'll add up to 1. You'd have 3 plus 1 is 4. So your last value you'd plug in would be 4. K doesn't actually appear in the integral though. K is just the counter, the first term, the second term, the third term. So K is 1, 2, 3, 4, 5, up infinity. Unless you set a top limit, like I said, 10. Or just go with 4 if you want. And if it's easier to think about, sometimes it is. Now, the trick here though is, if this matches this, then it's easy street. There's other ways of coming up with that, and I will. Let's look at the one below it, C, because it's a little more straightforward. Now, when I see this, just from what Mr. LaBelle was asking, 5, 1/2. Is it more straightforward? Yeah, it isn't as straightforward, is it?
What is the 2 in front of the k?
There's no exact match, is there? 3 plus 2k. Uh-oh. I'm going to just give myself a little more space. You could think of this as 3 plus k times 2 over n. Okay. K is the counter, 1, 2, 3, 4. What do you notice about, now I'm going to write this down temporarily, 1 over n. It's a mismatch, isn't it? This only works if we get this as an exact match. Son of a gun. What can you multiply any equation by? 1. How could I turn this by multiplying by some form of 1 so that this 2 over n matches that?
Why can't that be 2k over?
Well, we lead into some problems. It's easiest if you can imagine it somehow where this has 2 over n as well. Multiply by 1/2. Multiply by 2 over 2, really. So what I'm saying is that if I take this and multiply the original expression by 2 over 2, doesn't that turn that top with the numerator into a 2? Now I have a match here, but what happened to the denominator? I multiplied the whole equation by 2 over 2. I'm going to just move that out front. You could do that. You could keep it behind, too. It doesn't matter where you multiply it. This is trickier. And I don't know that you'll see too many like this, but if it doesn't match exactly right off the bat. So I'm going to take a look at this. Remember, I skipped, I was just only looking at this. It's still summation here, okay? So what is the integral? Starts at 3. Now we've got an exact match. We can say it starts at 3. What does the 2 represent, though? The blue 2 that matches the red 2 inside. It goes up by a span of 2, right? So 3 to 5. Where did I get that 5 from? Maybe I'll just write it down. The initial term plus 2. Because this has a span of 2 units divided by n. So if you're using an infinite. But if you want to, and it makes you feel better, just choose 10 to try things out, or 12 or something. So this is really 5 here, and I'm going to erase it and put 5 back there. What's the function? 5 halves, because we had to put that blue 2. And then, now, because this is a match, you could just consider this as single x. Okay? And this was just a counter. This part will never come into your, it's the first term, second term, that's what k is. So this is 5 halves root x dx. If I gave it to you in this format, not that it's easy, it would have been easier. I think you all would have figured out 1/2 for the root. If I would have given it to you there. That's not the only way that one could have been done. But that's one of the ways. Now, is there one you could do in a single step? Yeah. D. You should be able to just examine D after we've played around with the other 2. D is, I'll give you a minute. See what you think of D. Write down what you think. It's matching with 2n, 2 over n, 2 over n. So that makes life easier. You got something, eh? I hope. Now, I tried not to change too much other than the power of a half or square. Change only 1 or 2 things at a time. So what do we start at? 3. Okay. Because of this. We go up by 2 over n, so 2 more, so it's 5. Okay, we've taken account of the 3. We know the span. Big 5 in front. It still looks like radical x. Yeah? I think so. It is. I've worked out, like, some of these I have 4 different ways of working them out. I just played around. I invented the questions here, then I typed them up. And now do you see why up here I said let's take 0 plus 1/2, 0 plus 2 times 1/2? That's the k value, right? That's what I was getting at the start. This one here is it's a devil. There's a number of ways you can think of this one. I have 1, 2, 3, 4, 5. Because there's no direct match right away. I can think of 5 different ways of doing this one. Help me out, because there's... Okay, but we'd have to do it in the inside. Is that what you're thinking? Then, because this is already... Oh, I know which way you're thinking. You're thinking,
On the outside.
yeah, on the outside. Okay, gotcha.
Move it down to over the top.
Really and truly then,
It's the same as C.
why don't we, we don't even have to multiply by anything. Can you think of this as 2 times 1 over n?
Yeah.
What if I scoot that 2 out in front and make it a 10 up there? Mind blown. Okay. So I'm going to go with his suggestion. Here's one possible answer. I'm moving this 2 times 5s to make it 10. 3 plus k over n squared 1 over n. Now it's a match. Once you do that, you have a match, you can come up with an integral. Oh. It's the integral of, starting at, going up by 1 unit, 3 to 4, 10 x squared dx. That's one possibility. Now throw this out, and all of these can be thought of another way. What if the function was 3 plus x squared? 3, you know, within the brackets, or 3 plus x under the root sign. That's a variation. There's a way to come up with those too, and you'd start at 0 to whatever you want. But I won't go through it right now. There's other ways to think of these. And just because, well, this other last one is quicker. I'll do this and then stop and answer the question. Here's what you're likely to see. You're either likely to get one expression like this and say it is equivalent to which integral, a, b, c, or d, or you're going to get the integral and you say which one of these expressions, summations, is like this. Take a look. You don't have to actually work it out. I would scan quickly. Do they all start with 2 plus? Yes, they do. That doesn't help me. Are all cubed? Yes, they're all cubed. So that doesn't help me. So then I'm saying 2 to 6 is a span of 4. I'm looking for 4, and it has to match. This is the only one where the 4s match. Do you guys see that now? Starts at 2, has the cube, groups of 4 over n that match inside and out is the dx. So this d is the solution. Okay? The other ones, we could come up with the other ones, what they actually represent, but we don't need to. Okay, I'll leave it for here. Yep.
Is there like